Hey everyone, this is Tia Yusuf, and we're going to be doing a short video on, or I'm not going to say short video, we're going to be doing a video on KVL. And KVL is Kirchhoff's voltage law. In this video, we're going to go through a series of examples showing the theory behind this law, showing how we can apply it, how we can use it. And then at the end, we're going to do one example problem using KVL. Right here, I have a definition that we're going to be using of KVL. It's pretty common. You can find it on Google through multiple textbooks. And it's telling us in a closed path, the algebraic sum of all the voltages around any closed loop in a circuit is equal to 0. I know this definition can seem a little overwhelming, but hopefully after we go through all the examples and then the example problem, this will start to make more sense. So there's two key things I want to focus on first, and then we can work backwards. So I'm going to actually start at the end of this sentence. And a circuit is equal to 0. And saying any closed loop in a circuit is equal to 0. This is one of the largest things in this rule for us. So right here on the side, I just have a loop symbol, and then I have our voltages. And all I'm going to say, all of that is going to equal to 0, okay? Earlier, it says a similar thing, a closed loop path, that the algebraic sum of all the voltages, okay? So we're slowly breaking down this definition. So right now, all we have is all the voltages in a closed loop will equal 0, okay? And also it's beginning closed loop path, algebraic sum of all the voltages, okay? So algebraic sum is telling me, okay, I'm not just adding 2 and 4 and 6 and 8 and 10 or whatever. It's saying the algebraic sum. And remember, in circuits, we can work with components that have polarity, where the direction matters, where the voltage drop or the voltage difference and which way it is different to what matters. So this algebraic is important for polarity and direction. Okay? And so knowing this, we can actually make this first equation we have a little bit more specific to help us with other problems. So something else I can say is, okay, so in my circuits, I usually have a voltage drop and I usually have a voltage rise, okay? So if I added up all my voltage drops algebraically and all my voltage rises algebraically, they should equal 0. Most of the time, my voltage drops might be modeled as a negative number. So I might drop 5 volts across a resistor, and depending on the scenario that I'm talking about, I might have that as a -5 in my equation. So that could be like a -5 volts plus R1, and let's say I had a 5 volt battery. That'd be an example of how that equation could look like. Okay, so if we're assuming these voltage drops are negative in a sense, we can also rewrite this equation one more time. That might help a little bit more. So I can say the voltage rises should equal the voltage drops. And hopefully when I go to these examples, we can see how all of these equations play into each other, how they're similar, and how they should all coincide with the same central idea. Okay? So we talked about resistors, and they can oftentimes have a voltage drop across something. But we also have other components. We have current sources, we have voltage sources. So those can be our rises, or depending on the direction of polarity of that, it could be a drop. We have diodes, that could be a drop. That can be a rise depending on what we're talking about. So I'd say the algebraic sum is the hardest part of KVL. So let's make some steps for us before we go to these examples. First, let's find our closed loops. Loop or loop, there could be more than one. Let's first do that. Let's find our closed loops. Let's find which components are adding to 0, which components should equal each other. Let's determine how many of those components are in our loop. Is it a closed loop? Should we even mess around with it or use this rule? Should we take a different approach? Let's do that first. And then I say our second step, let's think about current. We don't have to find current values. We don't have to do anything with it. But let's just think about current, how it's interacting in our circuit, how that can impact what we might consider a voltage drop or a voltage rise. Okay, so we're going to start with this first example, and hopefully I can start explaining some of these ideas for us. But we first want to do a simple series circuit. So if I'm looking right here on this left-hand side, I have a simple series circuit. I have a 13-volt battery in series with R1, in series with R2, and then I have my ground symbol at the bottom right here. Okay, so this is a simple circuit. We're familiar with it, okay? And that first step I said is, let's find a closed loop in this scenario, okay? In this case, if I'm thinking about a closed loop, if I start at my battery right here, and I go through my R1, and I go through my R2, and then back around to my battery, in this case, this is my closed loop, okay? My closed loop is all three components. It is also the entire circuit. This is not always going to be the case, but that can be the case, and it does work for KVL. And so this should make sense, because if I think about what KVL is saying, it's saying that this 13-volt battery should split across R1, should split across R2. It should split across that combination of the two. This sounds familiar to that idea of a voltage divider rule that we had and what we know about series circuits. So this should make sense. So we have our loop. We have one loop, and now we have three components in that loop. So now let's try making an equation. And we can just let's try this first formula where we had our circle and we said all voltage values will equal 0. Okay, so 13 volts is what we had, okay, plus the voltage of VR1 plus the voltage of VR2 will equal 0. Okay, this is that first equation we just made. I said we had one loop and we have three components. We should be all set there. So that's our step number one. Step two is think about current. So here, if I'm thinking about my one voltage source, I know the direction that the current's going in. It's going to be going in this clockwise fashion, okay? And that means if it's going in this clockwise fashion, I will drop across R1, and I'm going to be dropping across R2 in terms of voltage as well. Okay, so I've made my first equation just based off what I had for my loop, and now I'm going to slightly modify it based off of what I've had after thinking about my current. So if I know that these R1s and R2s are going to be dropping as compared to my source, which is providing the 13 volts to my circuit, I'm now going to model it as 13 volts minus VR1 and then minus VR2, and this is going to equal 0. And that other form that I had from earlier that also works, I can say 13 volts equals, so this is my source or my rises, so I'm going to say rises equals my voltage drops plus VR1 plus VR2. Okay, so I talked about my loop, I talked about my components, and I also talked about different forms of getting to this equation. All of that looks good, all of that's great. But now a question could be, okay, I found a lot of information here, but I didn't find anything quite yet. And that's because in this scenario, we have two unknowns. A lot of times when we use KVL and we're trying to use it to solve for something, we really want to isolate that one variable that we don't know. In this case, it was just show us the theory and say, okay, how can we set up these loops? So let's say R2 was given to us as 3 volts. Now we can go back into our equation and we can see, we can use either or, 13 volts minus VR1 minus the 3 volts from VR2. And now I can see the use in this equation. I can see, okay, when I have one unknown, I can find the voltage drop across R1 is going to be 10 volts. And that's just using that algebraic sum. That's where we get it from our definition. So KVL can be very useful. It can be very helpful to us. We just have to make sure we know how we get there with our first 2 steps and then know what we're solving for. And something that we found the voltage of R1 without having any current values, without having any resistance values. So in some ways, it can be used in different scenarios than Ohm's law. Okay, that was our first simple series circuit. We're going to be doing the same idea with the simple parallel circuit. And like I said earlier, first step is find those loops. In this case, I'm looking at my simple parallel circuit. I might not have one loop. And it's saying it is one path, one complete path loop, okay? And that does not have to be the entire circuit. And what I'm seeing here is if I'm thinking about like that series path of one path, if I'm starting at my voltage source, I'm going around and then I go to R1 and then I'm back to my voltage source. This is my first loop right here, loop 1. And I'll write L1 right here, okay? And then similar fashion, let me go down my second branch in my parallel circuit. If I'm going from this 24-volt battery through R2 and back down, back to my battery, there's my loop 2. Okay. And then it looks like to me there is going to be one more loop for our circuit, okay? And this is this orange branch right here where I start at my battery and then I go to resistor 3. Okay. So now I've thought about my branches, and just so something I'd like to point out, none of these loops was the entire circuit. Loop 1 does not include resistor 2 or resistor 3, and loop 2 only does not include resistor 1 or resistor 3. And that's perfectly okay. KVL doesn't apply to the whole circuit, it applies to our loops of where the path is continuous, and we're looking at what rises, what drops in that circle, in that loop. Okay? So let's talk about this idea again. Voltage source equals the voltage drops, or voltage rises equals the voltage drops, or the sum of all voltages. So my first loop, I'm going to have two components. This is going to be my V1 and my R1. And this is actually going to be the same case for my other ones, but my resistor is changing. So for loop 2, I have two components. That's still V1, but it's R2. And then for loop 3, I'll have two components, V1 and R3. Okay. Loop 1, I have 24 volts, and then plus my VR1, and I'm saying this is going to equal 0. I've done my first step. I've thought about my loop, I've thought about the components, I've thought about the branches, all the possible loops I can have, okay? Now let's think about that algebraic sum part, okay? If I'm thinking about current, I have one voltage source. It's pushing it out from this positive end, positive terminal of the battery, and I should be dropping voltage across my resistors for R1, for R2, and for R3. Okay, that sounds good to me. So now I'm going to go back. I'm actually going to change this plus VR1. I'm going to say minus VR1. And this is perfectly fine for writing my equation in this form. It's still perfectly okay, because remember, we're talking about the algebraic sum. So those polarities matter, those directions matter. Okay? So in this case, I have my one unknown that I was talking about from earlier, and KVL is very useful here. VR1 will equal 24 volts. And this same equation can be used for VR2, and that same equation can be used for VR3. 24 volts minus VR3 equals 0. VR3 equals 24 volts. Okay? All of this looks good so far. Because this is a simple parallel circuit, I can actually check my answers to KVL and see, does it make sense with this parallel circuit? Remember, in a parallel circuit, that anything get parallel with each other, so this resistor R1 and R2, since they're parallel to each other, they should share the same voltage drop. VR1 is 24 volts, VR2 is 24 volts. In addition to that, they're all in parallel with my voltage source of 24 volts, so it should make sense they all have a drop of 24 volts. So right here I learned that KVL does agree with what I know about parallel circuits, and the previous example showed me it agrees with voltage divider and series circuits. Okay, I'm going to go back up top, and we talked about our simple parallel circuit, we talked about our simple series circuit. Let's move to a combination circuit. Okay, if I scroll a little bit down here, perfect. Okay, Here we have a little bit more going on, okay? And first, let's look at our circuit, and then we can talk about our loops, then we can think about current, okay? I'm going to change to blue, and let's talk about just the beginning of the circuit. Here, I have one voltage source, 18 volts. I have R1 right here. I have a second resistor. I have R3, R4, R5. Okay, this one looks a little bit more complicated than my previous circuits. It's not just series, it's not just parallel, but that is going to be A-okay for us, okay? So let's use what we learned from the last examples and how we can make these loops. Let's think about how can I connect my circuit if I'm going along one path and what these loops will be in this scenario, okay? So this first loop, I'm going to call it loop 1 and we're going to do it in blue, okay? If I'm starting right here, if I'm walking along this path, I'm going from my battery to R1 to R2 and I'm going back around. This is my first loop. And just like this first example, or just like the second example, this loop is not our complete circuit, but that's perfectly fine for us because we did complete a path, we got back to where we started, okay? And for this loop, I'm going to have 3 components. I'm going to write that right here, 3 components, okay? Now the second loop, I'm going to draw in green. Same idea, I'm going to start at my battery, but in this time, I'm going to take this path. I still go through R1. I'm not going through R2, but I go through R3. And this is going to be L2, loop 2, okay? That's my second loop. And then for my third loop, same idea. Let's start at my battery. Let's go through R1. We're going to skip R2 and R3. And instead, we're going to go through R4, R5. And this is L3 or loop 3. And this one will actually have R4, R5, R1, and 18 volts. This one will have 4 components for us. Okay? And then I'll make a note to myself here. 4. In my drawing of the little guy right here taking the path, I did in a way think about current and how that would work. But let's talk about that as well right here. So in this case, once again, it's only one voltage source. So I'm going to have the current going the direction it should. And all these resistors are going to drop accordingly. Model that as a minus sign. Plus minus, all these are going to be drops. Okay? So now let's start writing our equations down for our loop 1. So now that I'm starting to get the hang of it, I'm going to skip that step of where I had it separated. You can still do whatever is most comfortable to you, whether that's voltage rises equals voltage drops, or having them all start as positive and then think about current. Here, I'm going to say, okay, I have my 18 volts and I have 3 components for my loop 1. I'm saying minus VR1 minus VR2 equals 0. Okay? Same idea for loop 2. 18 volts minus VR1, but instead of VR2, I have minus VR3 equals 0. And then for the orange loop, the third loop, I'm going to have 18 volts minus VR1 minus VR4 minus VR5 equals 0. Okay. If I was given 2 other or 1 other voltage value, I could start with whichever loop I had that one unknown with. If they gave me VR1, I could start by finding VR2 and then work my way down with new information I learned. In this case, we're just setting up the equations, so it's not too useful to us, but it's good to see how this process can work and help us. Okay, now we're going to be moving down to our last example of where we can use KVL, how we can think about it, and how it can be useful to us. Okay? I didn't make any color coding on this document yet, on this last circuit, but this one's going to be telling us about how it can work in terms of nodal voltages. So far we've only worked with these voltage sources that were already given to us, but how can we use KVL to describe something a little bit slightly different? I've already showed in previous examples that KVL does not have to be the whole circuit, okay? I'll write that out again. be the whole circuit. It can be any closed loop where we start where we finished. Okay? In this case, we're given a voltage source right here. We're given 4 resistors. I have my R1 first. I have a nodal voltage at VA of 10 volts. And then I have R2 on this branch. And I have R3 and R4 on this branch. Okay. So that's a great start for me. Okay. So I'm going to start by, let's talk about the higher, I guess, like the higher level thing, and then we can go into the details. So if I was going to look at this circuit of, okay, how can I talk about it in the most simplest format for my first loop? I'd say I'd start at my battery, I'd go across this R1, and then I'm going to VA, and then I'm going straight to the end of my circuit, and then I'm going back around, okay? And remember, for nodal voltages, if I'm saying VA, that's applying that this is in respect to ground. So my loop here is going to have 1, 2, 3. I'm going to have 3 components or 3 expressions in this equation, okay? And those 3 for loop 1 is going to be E1, my voltage source, R1, and then VA. And then I'm going to explain this one more time just to make sure that we got it. So I'm saying I started at E1 right here at the top, and then I went through R1, and then I have this given known voltage value of how much I dropped from this point to ground. So in this case, my closed loop is not going to be talking about R3, R4, R2. I'm just going to be using my nodal voltage. So if I was to make this equation, I could say E1 plus VR1 plus VA equals 0. And that's that basic equation where I'm saying I need to talk about the algebraic sum and the algebraic polarities and directions. In this case, once again, it's still only one voltage source. My nodal voltage is not a voltage source. It's telling me how much voltage difference there is at that point. So I can model this as E1, and then there's a drop across VR1, and then the final drop is across VA. Okay? So I was to write that out. Let's say in this example, if they told me that E1 was 14 volts, I'd say minus VR1 minus VA, or 10 volts for VA, equals 0. I would be able to find that VR1 is equal to 4 volts. And that's a case of how we can use KVL in a different manner with these nodal voltages. I can also go a step further and think about what VA is talking about and how that can relate to its own loop. So, okay, if I'm looking at VA, I really have another circuit here. So I'm going to draw it again. Just on this side right here, I have VA just at the top here. And then it's going down to R3 and R4. And then we're looping back around to our circuit. Let's think about how we can make loops with this value. So R3, R4, and R2. VA told us there's 10 volts difference between here and from ground. That's telling me that, okay, if I have 10 volts here, R2 must make up a portion of that 10 volts. If this is one of my loops I'm thinking about. And that R3 and R4 should make up a portion of that 10 volt drop if that's one of the loops I'm thinking about. I'll do this in another color as well. So I'm thinking here to here. Okay, and I'll explain that one more time, okay? We know this nodal voltage of 10 volts right here. And we're still thinking about how can I form a closed loop? If I'm starting at this 10 volts, I'm going to R3, I'm going to R4, and then to ground and back to my 10 volts, I should have a case where I can apply KVL, okay? So I'm really saying 10 volts should be equal to the voltage drop across R3 plus the voltage drop across R4, and I'm also saying 10 volts should be equal to the voltage drop of R2, okay? So that's two separate ways that nodal voltages can help us in using KVL. we can model it as its own component, its own resistor, or we can also model it in a way similar to a source or similar to a known voltage value. And so instead of being an unknown factor, an unknown component, it can help us in determining a different value. Okay? So if I scroll back up, we're just going to verify and make sure I was able to talk about my simple series circuit. I was able to talk about my simple parallel circuit, a combination circuit, and also a nodal KVL circuit. The last thing we're going to do here is we're going to tackle this example problem, okay? And we're going to follow those same steps, and this is going to be meant to bring everything back together, okay? This is just an example problem for our textbook, so it should look familiar in the format and how the components are displayed, okay? So I'm going to write down our steps first. First thing, we're going to think about the loops, what we can make, how many components are in there, how many are there, okay? And the second thing we're going to do is think about current. Before then, let's see what's in my circuit before I think about the loops. I have E1, so I have a voltage source here. I have R1 with the unknown V1 voltage. They're giving me the voltage drop across R2. Okay, I like that. And then I have a second source here that has 9 volts across it. Okay. So I know what's in my circuit. I have two voltage sources and I have 2 resistors. Okay. I think I'm ready to start tackling this problem in terms of the loops and how many loops I have. Okay. Let's start at E1. Okay. If I go E1 to R1 to R2 to E2, I have one loop right there, loop 1, let's call it L1. In this case, this loop is in our entire circuit and it has all 4 components. Okay. I can also have a second loop here, and instead of starting at E1, why don't I start at E2 just for fun? So I'm going E2 to R2 to R1 to E1, and then back to this 9 volt E2. And this is going to be my loop 2. Okay. Hopefully with this example, we can see the importance of the algebraic sum in setting up both of these equations. Okay. So I'm going to take a step back to the very beginning where we just have this same equation with our little symbol, voltage equals 0. And that's how I'm going to set up these first equations. So if I go right here, loop 1, we set all 4 values. So E1 plus V1, we can say VR1 plus VR2 plus E2 must equal 0. And then let's also write loop 2. We said E2 plus VR2 plus VR1. E1 equals 0. Okay. So we did our first step. We talked about our circuit. We made our loops. Now let's think about the current. Okay. And in my mind, I see that this E1 is a greater value than 9 volts. So by instinct or by just what I personally think, I'm going to choose to put the direction in going clockwise. In loop 2, I will actually have the current going counterclockwise, and we'll see it doesn't matter which direction that I choose as long as I'm staying consistent with my voltage rises and my voltage drops. So let me write that here. This one's going to be going counterclockwise, and for our orange loop, we're going to be going clockwise. Okay? I'm going clockwise for this loop for E1, so I'm going to write it down here as well. Loop 1, I have 16 volts. That is my rise. It's my source. Okay? And I'm going clockwise. I drop across VR1. I drop across VR2, and that is a given value to me, 4.2 volts. Okay? And now I have this E2 voltage source as well. And now the question might be, am I adding it or am I subtracting this E2? How do I find that algebraic sum with this E2 for my first loop? And we can think about how it behaves in terms of the current. If I already said that I'm going clockwise for everything here, And if I'm going clockwise against it, I'm dropping. This source is pushing against it, so I am going to be dropping across this voltage as well. And I can even look at those indicators, the plus and minus are already indicated, and that also helps me, tells me the same thing. Okay, so this voltage source is pushing it in the opposite way, but I'm saying I'm going clockwise. I'm dropping from this positive 9 to below 9 minus. So I'm going to say minus 9 volts equals 0. Okay? 16 volts minus 9, and then minus my 4.2. The answer I should get is 2.8 volts, and this answer is VR1. Perfect. Okay? And when I do loop 2, even if I go counterclockwise, I should expect to have the same answer. So let's try that. Loop 2, I said I'm going to start. Okay, so for this loop 2, once again, I'm going to be going counterclockwise. I started with my 9 volts, and then based off the diagram, I see, okay, this side is lower compared to higher. So when I go counterclockwise, I'm going to represent this voltage drop across R2 as actually a voltage rise. So I'm adding 4.2 volts, and that number comes from VR2. Similar idea with VR1. And then I'm going to subtract my 16 volts. And this all equals 0. When I do this, I will get VR2 is equal to a negative 2.8 volts. All this is telling me is that that current assumption that I made in my loop is actually incorrect. So instead of dropping this way, I should really be modifying it to what it looks like already on the circuit, what they already stated. So my final answer would still be 2.8 volts. And I could say, if they asked about current, or if I want to redo what I had drawn, I'd say, okay, the actual direction of the circuit, of the current in the circuit is clockwise. Thank you so much for this video. Hopefully that answers a lot of questions about KVL. I say the two good things to remember is, remember, all voltage drops and rises should algebraically add to 0, and that KVL works in any closed loop. That does not mean the whole circuit. It can be, but does not always have to be. It could be a separate side branch. It could be a couple components. It could be a couple components with a nodal voltage. It can be a lot of different things. So make sure you think about those loops. Think about what components are touching current, where the current's going, and how that can impact the polarity or what to drop and what to rise. Thank you.